In this video, I will talk about the basic concepts of probability and counting. We will learn how to identify the sample space of a probability experiment and how to identify simple events. We will talk about the fundamental counting principle and how to find the number of ways two or more events can occur. We will distinguish among classical, empirical, and subjective probabilities. We will also discuss how to find the probability of the complement of an event and how to use a tree diagram and the fundamental counting principle to find probabilities. So a probability experiment is an action or trial through which specific results, counts, measurements, or responses are obtained. An outcome is the result of a single trial in the probability experiment. A sample space is the set of all possible outcomes of a probability experiment. An event consists of one or more outcomes and is a subset of the sample space. So let's look at this example. A survey consists of asking people for their blood types, A, O, B, and AB, including whether they are Rh negative or Rh positive. We're going to determine the number of outcomes and identify the sample space. So you know you have four blood types. You can either be a negative or you can be a positive. So let's look at this tree diagram. And as you can see, you can be O negative or O positive. You can be A negative or A positive. You can be B negative, B positive, or you can be AB negative, AB positive. So your sample space will be these 8 possible outcomes. A simple event is an event that consists of a single outcome. For example, tossing heads and rolling a 3. If you look over here to the side, I have a diagram of you tossing a coin and rolling a die. So remember, a die, a lot of people don't understand what a die is. It's just part of a dice. So when you roll dice, you're likely rolling 2 dice. So a die is just one of those dice. So you can you can flip a coin and get a head, and you can also roll a die. So you know you have 6 possible outcomes on a die. So you can get a head and a 1, a head and a 2, a head and a 3, all the way down to 6. Or you may flip a tail. So you can get a tail and a 1, a tail and a 2, all the way down to a 6. So tossing heads and rolling a 3 is just one outcome out of all these outcomes. So that will be considered a single event, a simple event. An event that consists of more than one outcome is not a simple event. For example, tossing heads and rolling an even number. So you can get a head and a 2, a head and a 4, and a head and a 6. So you have more than one outcome here. You have 3. We're going to determine the number of outcomes in each event, then decide whether each event is simple or not, and explain the reasoning. For quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So event A has only one outcome, and that's choosing the specific defective machine part. So this will be considered a simple event. The next one says you roll a 6-sided die, and event B is rolling at least a 4. Where when you roll a die, you have 1, 2, 3, 4, 5, 6 chances of getting whatever outcome. So if you roll at least a 4, that means you can get a 4, a 5, or a 6. So you have more than one outcome. This is not a simple event because you have more than one outcome. Now let's talk about the fundamental counting principle. If one event can occur in m ways and the second event can occur in n ways, the number of ways the two events can occur in a sequence is m times n. This can be extended for any number of events occurring in sequence. So in this example, you are purchasing a new car. The possible manufacturers, car size, and colors are listed in this table. So you can get a Ford, a GM, and a Honda. You can get a compact or midsize, and your color choices are white, red, blue, or green. How many different ways can you select one manufacturer, one car size, and one color? So let's look at a tree diagram. So you have 3 choices of a car. You have 2 choices of its size, and then you have 4 choices for color. So you have 24 ways to pick a car. So you can get a GM midsize red car, or you can get a GM compact green car. So if you count these all up, there's 24 ways that you can pick this car. The access code for a car security system consists of 4 digits. Each digit can be any number from 0 to 9. So we're going to answer the following questions, 1 through 3. The first one says, how many access codes are possible when each digit can be used only once and not repeated? Alright, so because each digit can only be used once, there are 10 choices for the first digit. Because if you think about it, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 10 choices. So let's say I pick 1. I pick the number 1. I cannot use it again. Cannot be repeated. So once I take out this 1, I'm left with 9 choices. I pick another number. Let's say I pick 5. I cannot put it back. That leaves me with 8 choices. Let's say I pick a 3 next. Okay, I pick a 3. This leaves me with 7 choices. My last one, let's say I pick a 7. Then I'm done. So the way you would calculate this is 10, 9, 8, 7. When you calculate it, you get 5,040. 5,040 possible access codes. Okay. The next question says, how many choices do you have if each digit can be repeated? Because each digit can be repeated, there are 10 choices for each of the 4 digits because you're not taking a number out. So once again, you have 0 through 9. You got 10 different ways you can pick the first one, first number. You got 10 different ways you can pick the second, the third, and the fourth. So when you multiply this out, you get 10,000 possible access codes. The next question says, each digit can be repeated, but the first digit cannot be 0 or 1. So if it cannot be 0 or 1, let's write out our possible choices. If it cannot be 0 or 1 for the first choice, excuse me, that means you only have 8 choices for the first number. The rest of the numbers can be any one of these 10 numbers, and it can be repeated. So this would be 8. You got 10 ways to pick the second number. You can put that number back. You then have 10 ways to pick the third number. Put that back, and then you have 10 ways to pick the fourth number. So when you multiply that out, you get 8,000 possible access codes. Now let's talk about the types of probability. We have classical or theoretical probability. Each outcome in a sample space is equally likely. So the probability of calculating this is the number of outcomes in event E divided by the number of outcomes in the sample space. For example, you roll a 6-sided die. Find the probability of each one of these events. So if you look down here, I have my sample space. When you roll a die, you have 6 sides. So 1, 2, 3, 4, 5, 6. What's the probability that you roll a 3? Well, we only have 1 3 out of the 6. So this would be 1 out of 6, or 0.167. I rounded to 3 decimal places. What's the probability that you roll a 7? Well, as you can see, there's no 7 in my sample space. So you cannot roll a 7 when you have only 6 sides. So this is 0. The next one says rolling a number less than 5. Less than 5 will be 4, 3, 2, 1. It says less than 5. So we cannot include 5 here. So this would be 4 out of 6, or 0.667. Another type of probability is empirical or statistical probability. It's based on observations obtained from probability experiments. It's the frequency of event E divided by the total frequency. A company is conducting an online survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So far they have 1,490 adults that have been surveyed, and this pie chart shows the results. Note that digital books include e-books as well as audiobooks. We want to figure out the probability that the next adult surveyed read only print books during the last year. So if you look at our chart, this blue part is how many read only print books. And as you can see, we have 578. We know so far we've interviewed or surveyed 1,490 adults. So the empirical probability will be 578 divided by 1,490. You get 0.388. In this example, a company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 social networking site users have been surveyed. The frequency distribution right here over to the right shows the results. We want to know what's the probability that the next user surveyed is 23 to 35 years old. So as you can see in this frequency distribution table, we have the ages broken up along with the frequencies. So we know we have 156 people that were surveyed were between the ages of 18 to 22. 312 were between the ages of 23 and 35, and so on. We want to figure out the probability that the next user is between 23 to 35 years old. So as you can see, that would be the 312, and this is out of 975. So to calculate this, we'll take 312 and divide by 975. We get 0.32. One thing that you should understand is the law of large numbers. As an experiment is repeated over and over, the empirical probability of an event approaches the theoretical or the actual probability of an event. So for example, we know that if you toss a head, you have a 50-50 chance. So you can toss a head or a tail. So tossing a head is 1/2. If you keep repeating and repeating, tossing a coin and noting its outcome, if you tossed 150 times, it should be half heads, half tails. Because that's the law of large numbers. The more you repeat it, the closer you will get to the actual probability. If you tossed it 10,000 times, your outcomes should be close to 5,000 heads and 5,000 tails because it's half and half. Now let's talk about subjective probability. And this is an educated guess or an estimate. A doctor may feel a patient has a 90% chance of full recovery. So this is just his educated guess. He really doesn't know. Okay. Now let's look at these examples, and we're going to classify these as classical, empirical, or subjective. The probability that you would get an A on the next test is 0.9. This is an educated guess. You really don't know what a person is going to get on the test, so this is subjective. The probability that a voter chosen at random will be younger than 35 years old, this is empirical. So this is most likely based on a survey. They says 35 years is 0.3. So once again, this is probably based off a survey. The next one is the probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000. So this is classical probability. Each ticket is equally likely to be chosen. So if you only have 1,000 tickets in the box and only one ticket can win, it's 1 out of 1,000. The range of probabilities fall between 0 and 1 inclusive. Okay, so if you have a probability of 0, that's impossible to occur. If you have a probability of 1, that is certain to occur. As you can look at the scale, 0.25, you're really in the unlikely range. 0.5 is an even chance. Once again, 50-50. 0.75, you have a likely chance. Now let's talk about complementary events. The complement of event E. The set of all outcomes in a sample space that are not included in event E is what you call a complement. And it's denoted, it's pronounced E prime. So if you took the probability of E plus the probability of E prime, you should get 1. And then you can use algebraic calculations to get the probability of E by itself. What you do is you subtract the probability of E prime from both sides. So the probability of E is equal to 1 minus the probability of E prime, and vice versa. The probability of E prime is equal to 1 minus the probability of E. So let's look at this table. We're going to find the probability of randomly selecting a social networking site user who is not 23 to 35 years old. Now there's two ways you can do this. You can actually just add up all the people who are not between the ages of 23 and 35. You can add those numbers up and then divided by 975. Or the quicker way would be to figure out how many are between the ages of 23 to 35, and as you can see, that's 312. We divide that by 975, we get 0.32. But we want to find the probability that they're not between that age. So what you can do is you can take 1 minus 0.32 and you get 0.68. So that's a quicker way rather than adding up all the other numbers. A probability experiment consists of tossing a coin and spinning the spinner shown. The spinner is equally likely to land on each number. We're going to use a tree diagram to find the probability of each event. The first one is tossing a tail and spinning an odd number. So let's look at our tree diagram. So you can get a head or a tail, and then when you spin the spinner, you can get 1 through 8. So you can toss a head and get a 1 on the spinner, or you can get a head and get a 2 on the spinner, all the way up to 8. Same thing for tail. You can throw the coin and get a tail and get a 1 on the spinner, toss a head and get a 2 on the spinner, so on all the way to 8. So the first question says, what's the probability of tossing a tail and spinning an odd number? So if we look at tails and the odd numbers, we got T1, T3, T5, T7. As you can see, we have a total of 6 outcomes. If we add all these up, we got a total of 16, and it's 4 that are tails and an odd number. So the answer is 1/4 or 0.25. Notice the key word here, it says and. If you look at this next question, it says, what's the probability of tossing a head or spinning a number greater than 3? So now we have an or. So you can toss a head and you have all your outcomes, H1, H2, H3, all the way to H8. Or a number greater than 3. You can toss a tail and get a number greater than 3. So that's 4, 5, 6, 7, 8. So this is not an and problem. This is an or problem. So you can either toss a head or get a number greater than 3. So as you can see, these are all my outcomes. That's 13 out of 16, which is 0.813. Okay, let's go back to the fundamental counting principle and how to calculate probabilities with this. Your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? So if we calculate this, there's 10 choices for each digit because the digits can be repeated. So you got 10 times 10 times 10 all the way up to 8. So it's 10 to the 8th power, or 100 million possible identification numbers. So only one of those numbers correspond to your ID number. So what's the probability that they get your ID number? We're going to take 1 over 100 million. And as you can see, it's 0 pretty much. It's 0.000 blah 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 all the way to 1. So that's very close to 0. That's the end of this lecture.